Hello, and welcome to our last lecture for the course Introduction to Data Analytics. This is Professor Nandan, and in this lecture I'll just briefly give you a summary of all the topics that we have covered during this course, perhaps tie some topics together. And in the last few minutes, I will try to give you some insights into what we will be looking at during the final exam. So first off, thank you for joining us. I speak for both Professor Ravindran and myself in saying that this has been a very valuable and enriching experience for us as teachers. One thing to understand is that this whole online learning teaching model is relatively new in the Indian context, and so for us as teachers as well as you as learners. But the hope is that we've been able to reach wider, and hopefully more people have been able to kind of get access to our content and are able to apply some of the things that they've learned in this course, either in their academic lives or in their jobs, their organizations, or maybe even their personal lives. But in any case, we're happy to have undertaken this endeavor, and from the bottom of our hearts, thank you for joining us. What this course in many ways tried to do is so this course was not a course strictly in machine learning. It was not a course strictly in inferential statistics. It was not a course in probability 101 alone. So in many ways we tried to give you the broad brushstroke associated with the entire landscape of data analytics. So in some sense, hopefully you're now familiar with a lot more terms and a lot more techniques and concepts than if you've taken a far narrower course. So the hope is that we've covered the breadth of data analytics, and it's never possible, of course, to cover the full breadth, but to a reasonable extent, the fundamentals and the basics of most concepts. We've also tried to go deep in certain areas, and it's primarily been more on the conceptual front, to give you insight into the hows and the whys and the whats of the different techniques. Why do some techniques work in some places? Why don't they work? What are things to watch out for, and so on and so forth. And so we also hope that it's given you a well-rounded enough knowledge to build upon further. So with this highly changing landscape of different software packages that come on different days, we've tried to make this a little less tutorial-like. We've given you some derivations, but this has not been fully about the theoretical math of the course, because the idea is that that kind of depth is something that, depending on your place of application and depending on your more specific area of use of data analytics, you should hopefully be able to build upon, given the knowledge that you've gained in this course. In this lecture, I'm going to go week by week and just talk about what we hope to cover there. But this is not, as you will see shortly, not just a list of each lecture and talking about it. So to some extent, the topics themselves are beautifully aligned with the list of lectures, but please do not think that each bullet point as I go from one week to the next is a comprehensive list of lectures. It's more the topics and the concepts. So I'll just talk to you a little bit about the broad topics and how they tie together, and in the last few minutes, as I mentioned, I'll give you some insight into the exam. So in week one, we really started off with a course overview, and the hope was both Professor Ravindran and I were able to give these long overview lectures. We had an intro lecture, and then I gave these fairly, I would say, long lectures that just tried to cover the entire landscape in 1 to 2 hours, and so hopefully that gave you some insight into what the overall course was about. The rest of the week was spent in descriptive statistics. Right, we talked about graphical approaches, so different ways of representing data and in this particular case with graphical approaches, you're really talking about different ways of visualizing data. An important concept that was also covered in this lecture was that data, it comes in different types, and we spoke about continuous data, categorical data. We spoke about, actually we broke it down as quantitative versus qualitative, and then quantitative broke down as continuous versus discrete, and then categorical broke down as ordinal and nominal. But that's an important concept that we kept on seeing at different points of the course. We moved on from visualization and we moved on to kind of individual statistics, right? Statistics that represent, or metrics that represent, central tendency. So those were the mean, median, mode. And then there were these measures of dispersion, so things like standard deviation, mean absolute deviation. And a lot of the time was not, so some amount of time was is spent on explaining how they work, but some amount on where they work and how they work, and why some are suited in some situations and others in other situations. We then moved on to probability distributions and inferential statistics. So we spent a good amount of time, introducing the concept of random variables as different from regular variables or constants that we are used to. So what does it mean when we talk about random variable, and how do you represent random variables through probability density functions, cumulative density functions, probability mass functions, and about how probability distributions can again be discrete or continuous, and how they get treated differently. We also spent some time in talking about a set of specific probability distributions. Namely, we spoke about the uniform, the continuous version, the discrete version. We spoke about the binomial, the Poisson, the geometric, the exponential, as well as the normal distribution, finally. In the latter half of this week, we moved on to inferential statistics. We spoke about this core idea where sometimes we have a phenomena that's generating data, and what you have is essentially a sample of that. What you have therefore in terms of data is a sample. The data is a sample partly perhaps because we were only able to access a part of the data, the overall data, or sometimes it's a sample because there's a broader phenomena that's creating this data and we've just taken a subset of that. And the core of this inferential statistics has been about how you don't just want to make statements about the data that you have at hand, but more about the underlying process that's creating this data. And that was our departure from descriptive statistics, and that's what we tried to motivate in those lectures. And we also spoke about this idea of single sample tests. So tests where you have a sample and the sample is coming from this broader universe, and how do you compare this to specific numbers or test hypotheses for parameters associated with the population. We then got deep into inferential statistics. So we went into two sample tests, the idea that you might have two sets of data that represent two different populations or two different phenomena, and how can you compare them. You can compare their means, you can compare their standard deviations, you can compare their proportions, and so on. And then we got into a lot of other concepts. So we spoke about type 1 and type 2 errors, the errors associated with saying that the null hypothesis is incorrect, or you're rejecting the null hypothesis when actually the null hypothesis was not incorrect. And the other error, the type 2 error, which is the idea that you fail to reject the null hypothesis when you really should have. We also extended that to confidence intervals, another important concept in inferential statistics, and we spoke about ANOVA, analysis of variance, and the test of independence. So with the ANOVA, we spoke about how you're able to frame more complex hypotheses, like the mean of population A is equal to the mean of population B is equal to the mean of population C, and so on. So with ANOVA and test of independence, really for the first time we were able to look at more than two states, more than essentially two samples, if you can think of it that way. more than two states of a particular variable. So up until the one sample and two sample tests, at most at two sample tests, you had this variable that could take on two possible states, and we would compare them. But for now you still are looking at categorical variables with the ANOVA, especially in terms of the input variable, but it's taking on more than two states. And with the test of independence, both the two variables that you're interested in, whether you want to think of them as input and output variables or just two independent variables, two variables could take on two or more states, and you're interested in seeing if these two variables are independent of each other or not. We also used this week to come up with a short introduction to regression. Right? What is regression all about? What is it trying to achieve? And what kinds of problem statements do we address in regression? A part of the focus has been about talking about how typically the input and output variables associated with the regression are continuous quantitative variables, and how this process of regression gets used for prediction as well as interpretation of the relationship between the input and output variables. We then choose to introduce machine learning, and the whole idea of mixing up the regression process and the machine learning process was very carefully thought through, because machine learning being a relatively newer field than regression, but also one where a huge subset of it, which is supervised learning, really focuses on many problems that regression at one point tried to do, and perhaps does it much better. But to kind of not think of them as isolated topics, but to think of regression very much as one of the tools in the toolbox of machine learning, irrespective of when they came into prominence, was important. So many of the concepts in machine learning just as equally applies to regression. So we introduced the idea of supervised and unsupervised learning, where with supervised learning we said there is this notion of an explicit output variable that you're looking to predict. Often the way it's formally defined is that it's labeled data, whereas with unsupervised learning you have unlabeled data, or basically there is no one single output variable that you're trying to predict or to classify. We then were able to go back to the regression and talk about using the ordinary least squares regression. We saw a derivation associated with how we get to that, and we also spoke about how we can do regression in Excel and MATLAB, what are the various concepts associated with it. We spoke about the idea of using backwards and forwards stepwise regression, best subsets regression, and so on. We then went on to a concept that's very important with regression, called regularization and coefficient shrinkage, but it's in some sense extendable to other methods. But we focused it more on the regression front, and the idea with the regularization was, how do you focus on models that don't wind up overfitting the data, because you can always introduce enough complexity into the model, make the model so complex that it winds up doing a very good job of representing the data at hand, but it doesn't really do a good job of it really doesn't do a very good job of predicting new data, because all the complexity and all the use of many variables, more than those required, they wound up getting used to kind of just overfit the data, to just do an exact replica of the data. Highly related to that is also the concept of coefficient shrinkage, especially when you have a couple of variables that are highly correlated to each other, a couple of input variables that are highly correlated to each other, and we call this the problem of multicollinearity, and how there are methods for coefficient shrinkage like ridge regression or lasso regression, which attempts to not allow coefficients to balloon in typically opposite directions in an effort to kind of better represent the data. We also gave you some insight into the whole data modeling versus algorithmic modeling ideas, and the core concept that we were trying to instill there is we introduced a new approach called the k nearest neighbors, and contrasting the k nearest neighbors with the regression based approaches really spoke about how with some approaches, which we're going to call the algorithmic modeling approaches, you didn't have to have an explicit mathematical model, and in fact it was better represented by a set of algorithmic instructions rather than a mathematical model that connects the input to the output, or at least the mathematical model is not constricting the potential relationship that the input and output variables could have, because an algorithmic representation could be more flexible in terms of representing this relationship. And the KNN versus regression hopefully captured that dichotomy. In our next week, we focused on supervised learning, which is, as we just previously discussed, this area where you have an explicit output variable and you're really trying to predict that output variable. And as you can see in this set, and this is a commonly used nomenclature of having regression and classification techniques. Here the word regression, unfortunately, while it's being used, really means problems where the output variable is continuous and quantitative rather than discrete or categorical. And for those where the output variable is discrete or categorical, you had these classification techniques. And in that light, we spoke about logistic regression and support vector machines and your decision trees. Now, all of these techniques definitely work as classification techniques, while classification and regression trees can do both regression as well as classification. With logistic regression, we introduced the subject. We also taught you how to train a logistic regression classifier. Similarly, with classification and regression trees, also known as CART, or more broadly, CART becomes the algorithm. The decision trees are just a way of talking about such trees. Support vector machines was also introduced along with some derivations on how the classification through the support vector machine happens. And the core concept there being that you're really creating this hyperplane and you're trying to maximize the distance between different classes to the hyperplane, which is actually splitting the input space, thereby enabling you to build a classifier. And we also spoke about the case where you have some kind of violations where some data points of one class overspill to the other side of the hyperplane, and the case where there are non-linearly separable data, and the use of kernel transformations. Now, we also spoke about this concept of the bias variance dichotomy, and the bias variance dichotomy talks about the concept of overfitting versus underfitting, where the idea is that there is a sweet spot in terms of the model complexity for a given data set, for a given underlying relationship between input and output variables. There is a sweet spot in terms of the model complexity, and when you have too little model complexity, you're essentially building a regressor or classifier that is bound to have a high amount of bias, which means that irrespective of how many times you repeat the process with different data sets, you're always going to be chronically underrepresenting or overrepresenting certain regions in the input space in your process of prediction. Now, when you move to the other side, which is you have a model that's too complex, you've overshot your sweet spot for this given data set, for this given underlying relationship, you are essentially likely to create a model with high amount of variance and a low amount of bias, which just means that each time you do this task, you're going to get a completely different model. On average, if you were to do this millions of times, the average of all your models might not have much bias. So you're not chronically underrepresenting or overrepresenting sometimes. You just don't know what you're going to get each time you do it. And so at a given exercise where you have a given data set and you're choosing to build a model, it could still be a really bad model. And so this is known as the bias variance dichotomy, and it that really segued into the idea of how do you therefore evaluate models and therefore select models. And in that light, we spoke about some of the metrics that penalize model complexity beyond a point, because you can use that penalization in conjunction with trying to do the best job you can of fitting to the data to come up with that balance. But we also spoke about some more computationally intensive but more effective, I would say, techniques like cross-validation, which don't just do a blanket penalization based on complexity, but instead allow you to hide some data away, build the model on other data, and then try to actually do the job of predicting on this new data set, and essentially do this kind of out of sample validation, and then thereby make decisions on both the complexity and the type of model. A small note on the use of linear discriminant analysis and the quadratic discriminant analysis. You can also think of them as methods. Those were essentially this is the last bullet point that I'm talking about. We made a careful decision not to actually include those lectures. If you look at this week, this was a very packed week with a lot of content and way more hours and lectures. And so while this is included in the syllabus, we made a conscious decision not to give out lectures in this topic. And that's partly because we had discussed a lot of very important classification techniques, relatively, I would also say, more popular ones. But to just give you some insight, the way linear and quadratic discriminant analysis works is that it tries to create a distribution, a multivariate distribution, essentially, in the input space associated with each class, and come up with a decision boundary based on the probabilities associated with this multivariate distribution of each class for a given input point. So we don't wait to actually ask the question of each multivariate distribution. We instead create these multivariate distributions for each class, because this is primarily used in classification, and it's a multivariate distribution in the input space, and we basically come up with decision boundaries, and these decision boundaries are linear or quadratic, but essentially you come up with these decision boundaries based off of the distributions you built. So right off the bat, tomorrow when someone comes and says, here is this input, can you classify this for me, you can see on which side of the boundary this falls. And more often than not, the typical approach is to use the multivariate Gaussian or the normal distribution. And an important distinction between the linear case and the quadratic case has to do with the assumption of equal variance. So if you make the assumption of equal variance, you're essentially using linear discriminant analysis. If you do not assume equality of variance, you're using quadratic discriminant analysis. Okay, so in the next week, we really took on some more advanced topics in supervised learning. We spoke about the use of ensemble methods, and more specifically, we illustrated that with random forests. The idea behind ensemble methods and random forests were really to do with the idea that you can sometimes have a deterministic algorithm on a given data set, but sometimes it really helps to inject some form of stochasticity either in the algorithm itself or in the data, and thereby create multiple versions of this algorithm. More often than not, it's in the form of versions of the same algorithm, but sometimes you can also have completely different algorithms that are trying to do the same job. But the idea is that you create multiple versions and then you aggregate their predictions, whether the predictions are regressions or classifications. You try to kind of aggregate them to come up with one final prediction. And this sometimes helps, especially this helps in these methods where a fairly greedy algorithm has gotten stuck into some form of suboptimal, right? Because as you would have realized by now, a lot of the machine learning techniques rely on optimizing some function or the other, whether it's support vector machines, whether it's ordinary least squares regression, or whether it's classification and regression trees, you're at some point trying to optimize some function, and thereby improve your ability to predict. But as with any optimization, the most common thing that gets discussed is getting stuck. And sometimes this kind of ensemble approach, where you just forcefully introduce some noise into the whole process, helps you break out of that, and overall prediction kind of improves. And we spoke about how random forests is one way of doing that with classification and regression trees. We then addressed the topic of artificial neural networks, an extremely popular and becoming even more popular approach to machine learning and predictive analytics. We introduced the topic in terms of how artificial neural networks are constructed, what is their motivation or inspiration. We spoke about how we can use the backpropagation algorithm to construct the artificial neural networks, and we finally took it towards deep learning. In reality, it's essentially just this neural network with many layers, and these really new and innovative techniques of actually being able to do the computation and the math to create such elaborate networks, which was previously not really feasible more than anything. We move on to week 7, where we talk about association rule mining and big data. With association rule mining, we spoke about this in the first context of it being there were two topics in unsupervised learning, and one of them was association rule mining, the other being clustering analysis. We introduced the idea of association rule mining and spoke about its fairly most common use case, which is the market basket analysis. The idea that you can create this table where the rows represent various instances or transactions that have happened, and the columns really represent features, and what you have is essentially a binary table of how frequently these attributes or columns have been seen with each instance. And with association rule mining, you're really trying to make a statement not about the rows themselves. You're using the rows, you're using the instances, but to make statements of the form that typically when column A occurs, column B also occurs. In the market basket context, which envisions a supermarket, you're really saying things like the rows here are people making actual transactions of purchases, and the columns are the different products that they choose. So the end result being that you want to make statements like people who bought coffee also bought milk, or more complex things like people who bought coffee and milk also bought sugar. So associative rule mining is useful there, and but it really extends. It extends to any context where you can create such rules, and it extends to any context where you have instances as rows, features as columns, and you really have a binary data set in that sense. We briefly spoke about different ways of measuring how good a rule is, and these are called interestingness measures, and some of the other challenges that are associated with scaling association rule mining. Finally, we spoke about a buzzword that we've all been hearing about, and this really spilled a little over week 7 and week 8, right? The whole idea being that we've heard this word big data. How is that different from the broader topic of just data analytics or data science in general? What this means, and why is it that we're seeing? What do we mean when we say big data? Does it just mean volume? We've heard other V's associated with it: velocity, variety, so on. We've also spoke about how some of the challenges with the regular techniques take on a different form with big data. When you have a much larger data set, what are some of the computational challenges that are associated with it? Are some methods more amenable than other methods? And how do you scale up such that you're able to actually process a huge amount of data and still get insights from it? Finally, in week 8, we presented clustering analysis, one of the other unsupervised learning techniques, and we spoke about how this is used primarily to segment data, to take unique instances and group them together. So here, in some sense, you have this data set which is represented by these instances or transactions or whatever it is that you want to think of as rows, and these rows share a common set of features. Now, based on the common set of features that they share and the different values that they take up with respect to these common set of features, you want to create clumps or groups or segments or clusters of your data points, of your rows, and the different ways of going about doing that. We spoke about some core concepts associated with clustering, but we also introduced two concrete methods, the k-means and the hierarchical forms of clustering, and how they work and why they work and so on. Towards the end, we spoke about some amount of prescriptive analytics, and the idea here was that sometimes you don't have data, and this lack of data could mean that you do different things, different forms of analytics, or I should rephrase that, sometimes you don't have enough data. And actually, a small correction, this should not be predictive analytics, this should be prescriptive analytics. Going back to my point, you either don't have data at all, or you have very limited data, and in some sense you have some control over what data it is that you're trying to get a hold of. So in the case of experimentation, much of the focus is on figuring out where in the input space do you want to generate data. Or another way of rephrasing that, or another completely different way of looking at it, is can you go about systematically and purposefully making changes to your input space? And by changes, we just mean setting it to some value and then getting a data point, getting an output associated with that. Now, that has a lot of advantages, right? Because you can get rid of problems of multi-collinearity, and because you're very carefully choosing where you're getting outputs, you're able to analyze the data much better, or with far more limited data. And that's the same whole premise of active learning as well. Active learning starts more from a space of saying, I might have some results already, but can I go about sequentially querying the system and choosing one at a time, sequentially, rather than a parallel deployment of 10, 20, 30 data points. But can you give me, based on the results, based on the outputs that I see, I'm going to come back to you and say, can you please give me a data point at this point, and get an output specifically for a given region, and update your model or update your system based off of that. And again, the whole premise is that you should now technically need a lot fewer data points to learn about the system or to model the system than a traditional system where you only have observational data. You had no choice or right in saying where you got your labels, where you got your output variables, which points in the input space, for which points in the input space did you get your outputs. This also links a lot with reinforcement learning, where again you have a say in which points of the input space you get an output, but here the output carries some value. The output is essentially also seen as a reward, seen as some form of online experimentation, where online here does not refer to the internet, but as much as online refers to this idea that whatever it is, the output that you're getting, the sole purpose of you doing this querying of the system is not to just learn about the system, but it is also to maximize some reward from the system. So you're essentially live. You can think of it in many contexts. You can think of it in a manufacturing process. You can think of it as a website, or anyone who's choosing to experiment, but they're experimenting with a real system, a system that is actually creating products and services and tasks that are actually going to the end user. So how do you go about experimenting on such a system where at the same time as you wanting to learn about the system, you also want to provide your end user with the best service or the best product? So how do you go about experimenting to learn, but at the same time also to do as well as you can while you're experimenting? Hope that gives you an overall picture of the course itself. In terms of the final exam, we're really looking at an exam where you're given about 30 to 40 questions, and they're all going to be multiple choice. And we've had some concern from students in terms of the types of questions, and the one thing that I wanted to kind of emphasize is that the questions themselves will not need you to do a derivation, partly because they're multiple choice. We're not going to say, here are the first 5 steps of the derivation, what's the next step kind of questions. Derivations are important, but they're important in terms of, from this course's perspective, that you understand how they're done and why they're done, what is it that you're deriving. And so in some sense, a lot of the questions themselves will be conceptual. You're not going to get like a fill in the blanks that says what is the next step of the derivation. And we're going to focus more on the conceptual part of the course's content. And in some sense, the whys, the whats, where do some methods work, where don't they work, what will be the likely outcome if I do a particular method on a particular data set. So they're very, very conceptual, and therefore any amount of working out is going to be more back of the envelope. So you can pretty much take pen on paper and you should be able to work out some stuff. And calculators are fine, but nothing. You really don't need a computer for much of this, and there are, I would say, fairly limited number of questions that require you to actually put even pen on paper. Most of them have to do with how deeply you've understood the concept and how deeply you've understood how the methodology works, or how a particular concept manifests itself when you carry out a methodology. And so I don't think you should have too many worries about doing complex derivations or doing complex math to figure out the right number. Focus, I would say, more on understanding the concept associated with, be it a methodology, be it a machine learning concept, be it inferential statistics versus descriptive statistics, or be it a derivation. Focus on the concept than in some sense the details. And finally, good luck. Good luck for your exams, and we look forward to having this kind of engagement and interactions with students going forward. Thank you.